An Introduction to Nonlinear Dynamics. This section will be much more conceptual than we've seen in the previous units, and really I want you to get an overview of what we can expect when we have a nonlinear system versus a linear system. We're going to see here that nonlinear systems become much more complicated than the linear systems that we've looked at up until now. And we'll see why we focused on the linear systems, which we can analyze using the tools that we looked at the previous 3 units. But once we have a nonlinear system, there's much more advanced tools that we need to be looking at. And also the consequences of nonlinear systems are much more different, much more complicated than we saw with the nonlinear systems. So the takeaways from this section I want you to look at is how do the nonlinear systems behave differently than any linear systems that we've saw before. One big thing we want to keep in mind is that the trajectories or the behavior of the nonlinear systems may be much more sensitive to initial conditions or parameters than a linear system is. We're going to introduce the phase plane for 2 dimensions or phase space for 3 dimensions as a way of analyzing the relationship between our state variables. So we're going to see how is it created and what can it tell us about the dynamics of our system. And we're going to look at chaotic systems, which only appear for nonlinear systems, chaotic systems, and how chaos is going to be different than random. So let's begin with a little bit of background into continuous nonlinear systems. These are going to be systems that we can represent using an ordinary differential equation. However, it's going to be a nonlinear ordinary differential equation. Later on, we'll talk about discrete systems, which are going to have different rules. We cannot represent them with ordinary differential equations, yet they are still going to be nonlinear systems. So the first thing, when we encounter continuous nonlinear systems, we are going to be representing them in state space form. So we're going to have to choose our state variables. We're going to need to isolate the derivatives of those state variables, just like we've done before with the linear systems. However, the way we're going to be solving them numerically, we're not going to be putting them into that matrix form. We're not going to get this A matrix, this stability matrix, because we can't form it when we have a nonlinear system. And for nonlinear systems, transfer functions are typically not going to work as well, so I'm not going to do any of this analysis in transfer function form. I'm going to stay entirely in state space form. Now, the analysis methods that we talked about in really Unit 2 are not going to work typically for nonlinear systems. So those analytic methods for knowing what's the overshoot, things like that, not going to work out for us. We're going to rely for this section, for this course, just looking at numerical solutions using typically ODE 4.5. And for many nonlinear systems, a solver like this is going to work either ODE 4.5 or 2.3, depending on the makeup of the system. We might be able to numerically solve it pretty decently, and we'll see that for the examples we go through here. Now, there are other methods to do a little bit of analytic work when we have a nonlinear system. One thing we typically can do is we can linearize a nonlinear system around equilibrium points. And what we're doing there is we're saying as long as our system states are operating near an equilibrium point, and near is very vague in its definition here, but if we're near an equilibrium point, we can linearize the system and we can analyze it as though it's a linear system when we're near that point. And then if we're near a different equilibrium point, then we have to linearize around that point. We're not going to talk about that in this course, but that is one way that we can analyze a nonlinear system, is by making it into a bunch of linear systems, which we do know how to analyze from Unit 2. Another thing you can do is averaging methods to see how our dynamic system is going to behave. Again, I'm not going to get into this in this course, but these 2 topics, linearizing our systems or using averaging methods, you would talk about in a more advanced nonlinear course. For this one, again, we're going to stick with just numerical solutions. We just want to see conceptually how nonlinear systems are behaving. We're not going to get too deep into the analysis of them. And in our nonlinear systems, some of them, including the Lorenz system, which we're going to really focus on here as our example, may be chaotic. I referred to this earlier, but what we're going to see sometimes in nonlinear systems is that the behavior of the system can be very impacted by the initial conditions or the parameters in our model. So even a small change in our initial condition can lead to a very large change in the response. And we call this a sensitivity to initial conditions, although it can also be dependent on the parameters we use, and we'll investigate both of these in our examples.